Okay, I'm recording this on my cell phone in my office, and I want to show you Faraday's law of induction in action. What we have here, this device here is a galvanometer, and even though it's not centered exactly at zero, part of that has to do with the angle of the phone, but it's also not exactly at zero. But even though it's not centered at zero, you can see that there's a needle in the middle, and it can go one way or another here, back and forth. What it does is it registers very small amounts of current, and hooked up to the galvanometer are these terminals. You could hook up a power supply here. You can see there, maybe you can see that there's two wires going up to the galvanometer that come down here. But then we're not going to use the terminals because the galvanometer is also hooked up to each of these coils here, and each of these coils has lots of wire that's been wrapped around a plastic core here. And inside the plastic core, it's hollow. So you can see my finger goes all the way through there in each one of those. My finger's not long enough to go through that one. But those are hollow. Now, I also have here an old school bar magnet, and you can see it's got a north pole and a south pole on it. And I'm going to put the bar magnet into each of these coils, and I want you to watch the galvanometer as I do this. First of all, I'm going to put the bar magnet in the small one up here. Let me readjust things. Let's put the bar magnet, the north pole of the bar magnet, in the small one. Now, watch the galvanometer. Maybe you could pick up that it is moving, but I'm going very slowly here. Now I'm going to pull it out, but I'm going to pull it out more quickly. Did you see something? Did you see the galvanometer deflect to the left? Now I'm going to put it in more quickly. And when I did that, the galvanometer deflected to the right. So pulling it out, pulling the north pole out, it deflects to the left. Putting the north pole in, it deflects to the right. But you'll also notice if I pull it out slowly, there's almost no deflection. In fact, I can see the needle wobble a little bit, but that's about it. Okay, so once again, in fast, to the right, out fast, to the left. But if I turn the magnet around, now I've got the south pole. Let's see. In, deflects to the left. Out, deflects to the right. In, deflects to the left. Out, deflects to the right. Okay, well, what about if I have more loops of wire? Does that change anything? Well, here we go. There's the north pole going into this loop of wire. So, oh, it deflected more. So it was easier to get a deflection out of that. Okay, and let's do this one now. An even bigger deflection going in, an even bigger deflection coming out. So deflection to the right, in, to the right when it goes in, and to the left when it comes out. So what you can see here is that the deflection depends upon how many loops are in this coil of wire here. Obviously, we get a much bigger deflection with this larger coil here. All right, but the deflection also depends upon the polarity of the magnet here. So let's turn it around and see if it holds for this big magnet down here. So wait a minute, which way was it? In, to the right, out, to the left. In, to the left, and then out, to the right. So you can see the polarity plays some role here. And I don't know if you've noticed this, but this is kind of an important part of Faraday's law, and that is the speed with which you move this magnet in. Notice I'm moving it in kind of slowly, and I'm not getting any deflection. I would expect a large deflection for this loop because it has the most wires, but the speed definitely matters. So if I pull it out of the coil slowly, almost no deflection. Okay, so what's going on here?